All right, so now that we've worked our way through equilibrium, we're going to look more at rotational motion, meaning objects that end up rotating around some sort of axis. So I pulled this picture from one of the previous conceptual questions I asked. We have a bar. It is fixed in the center here. There's some sort of axle that goes through it. So this bar can rotate around that central point. We hang this mass over here from it, and when we do that, it causes rotation, causes the bar itself to rotate counterclockwise. That's what this curved arrow is representing. So there is a net torque on this bar. Now the bar, besides the weight, this hanging mass, mg, it has, theoretically, I assume it has its own mass. So we would say mass of the bar, so mg for the bar itself, would be in its geometric center, because that's where the center of mass would be located. But if that is also the rotation axis, there's no torque due to the weight of the bar because r is 0. Any force acting on the rotation axis, so exactly where it is, or pointing towards the rotation axis, will not produce a torque. So the only force that is causing a torque in this case is the hanging mass. We can say the torque, if we draw in the lever arm, it points to the left. We would say the torque is half the length of that entire bar times mg, where m is the hanging mass. So at this moment in time, the torque will be 1/2 L mg. That torque causes the bar to rotate. Now, if you happen to remember, as the bar rotates, r is still half the length of the bar overall. mg still points downwards, but the angle is going to get bigger and bigger and bigger, until eventually the rod or bar will be vertical, the mass will be straight down. The torque at this moment will be 0 because r and the force mg are parallel to each other. The line of mg goes through the rotation axis. That's what makes r and the force parallel, and thus no torque, no twist. The torque at any point in between will be half the length of the bar, mg, times the sine of whatever that angle happens to be at the moment. So the torque is changing, but there is a torque until the bar is vertical. So we want to be able to relate this torque to the motion. As the bar rotates, if you remember, as we started chapter 12, we talked about angular quantities, angular position, angular velocity, angular acceleration. As this bar falls, it's moving through some sort of angle. By the time it is vertical at the bottom, it has moved through 90 degrees exactly, which of course we would want in radians. Theta is this angular position, though if we're going to use equations that have theta in it, we do need that angle to be in radians. Angular velocity is our omega. That's radians per second. omega is going to be changing because the rotation rate of the bar is going to be increasing. The bar is going to be speeding up, or I should say rotating faster and faster. Its rotational speed is increasing until it gets to the bottom. That means there is an angular acceleration in the same direction as the angular velocity, which in turn is causing it to rotate faster and faster. The units of alpha, we need to be in radians per second squared. So just as a reminder, at any given moment in time, we could talk technically about angular position, angular velocity, angular acceleration. Okay, let's relate torque in general to our acceleration. The net torque on an object. Well, if we go back and think of Newton's second law, before we said the net force on any mass will equal the mass of that object times its acceleration. We can think of like that bar as a whole bunch of pieces of mass. Each of these will be little pieces of mass. Technically, we would call them infinitesimally small pieces. Ultimately, we're saying that torque, now this is a very crude derivation, by the way. We're saying that torque is R times F, technically, specifically, F perpendicular. So if I multiply both sides by R, this is totally simplified, approximated, just to show you where the equation comes from. This left side now is torque, but each piece of mass, a piece of mass closer to the rotation axis, will have a different acceleration, A, than a piece of mass out here. These are the tangential or translational accelerations. Each piece of mass will have a different acceleration because they're different distances from the rotation axis. But we also have a relationship to relate this translational acceleration to angular acceleration. So if I put that in over here, I end up with R squared times alpha. The net torque is equal to a quantity that we use a symbol I to represent. It's called the moment of inertia. Another term for that is also called rotational inertia. And then the resulting angular acceleration from that net torque is dependent on the net torque, but also on this I, this moment of inertia. The I is representing these mr squareds. Well, technically we can't say mr squared because each piece of mass down here is a different distance away. So ultimately, to find the moment of inertia, we have to integrate. We need to say that each of these pieces of mass are infinitesimally small little pieces of mass, dm, and we have to account for how their position changes from the rotation axis. So technically, I is an integration, which we're not going to do. It is along the lines of a Calc 2 problem. you will calculate for rotational inertia in statics, at least to some extent. In our class, our author has done this integral for us for a number of common objects, which I will show you in just 1 second. If we say I is equal to exactly mr squared, this is true only if all of the mass m, that's not an m, is the same distance r away from the rotation axis. So something that would be true for would be a ring. For example, a ring, like a wedding ring that's just a band, or even something like a hula hoop. The ring itself, the rotation axis is in the center. Each piece, anywhere I go on the ring, any piece of mass is the same distance r from the rotation axis. And so we could totally say the rotational inertia or moment of inertia for a ring would be the mass of the ring times the radius of the ring squared. We will use this approximation as well for what we call a point mass, meaning a very small object compared to how far away it is from the rotation axis. Distance from rotation axis. Okay. As far as the integration is concerned, I'm going to grab the table from the book and copy it in here. So the table from the book looks like this. I'll make it a little bigger. This is in chapter 12. It is not something you need to memorize, but we do need to know how to use it. So the equations, this table is also in the test notes, but without the picture. So make sure you're familiar with the pictures so you also know what it means for each equation. So like a cylinder or a disc about its center. You can see each of these have a line drawn that represents the rotation axis. Where the rotation axis is essential to know. So not only for torque we had to know where the rotation axis is. Talk about the lever arm, R. But the rotation axis is also important in terms of knowing how or where the object is rotating around. So when we say that the net torque is equal to I alpha, this is the rotational motion version of Newton's second law. For a single small particle, the net force was equal to ma. The acceleration, a object that we were pretending was a point mass, the resulting acceleration depended on the net force, but was also inversely related to the mass. So two objects with the same net force, but different masses experience different accelerations. A more massive object required a larger force to end up with the same acceleration as a smaller object. In terms of rotation, that's similar. the resulting angular acceleration an object experiences is going to be directly related to the net torque acting on it, but it will be inversely related to this I, which is what we call the moment of inertia. It's also sometimes called rotational inertia. So the author has been kind enough to get these known values into a table for us to use so that we do not need to integrate every time we try to solve a problem. If you notice, in every single equation, there's an m for mass. So the moment of inertia still does depend upon mass, but every equation has some sort of dimension squared. On this right side, it's always an r, meaning the radius of the cylinder, the radius of the ring, the radius of the sphere. On the left side, it has L, or A, L meaning the length of the rod, or A meaning the width of this plane or slab. So this bottom left example would be like any of our doors. The rotational inertia of any of our doors depends upon the mass of the door and how wide the door is. Not how tall, just how wide. So this rotational inertia is not only accounting for mass, but it is also accounting for how the mass is distributed. Each of these, when we see L squared or R squared, it turns out that how the mass is distributed is actually a bigger factor than what the mass is. So the more the mass is distributed away from the rotation axis, so farther mass is from rotation axis, on average, gives the biggest I. Meaning, if we come back to Newton's second law, the biggest I for a given net torque would be a smaller angular acceleration. You can think of moment of inertia, the bigger moment of inertia is, the bigger I is, the harder it is to change the rotation. You need a bigger torque in order to accelerate something with a large I compared to something with a smaller I. So I, this moment of inertia, is a resistance to a change in rotation. A bigger I resists change in motion, and specifically rotation. So if I were to compare just a ring and a disc, notice I for the hoop, or hoop is the same thing as a ring. I is mr squared here, whereas a solid cylinder or disc is 1/2 mr squared. The hoop is bigger, meaning a ring will not accelerate as quickly as a solid disc will, given the same net torque. It turns out all of our motion equations, so like we see with Newton's second law, we're going to talk about energy and momentum as well. All of these equations will have I, rotational inertia, in them. So become familiar with this picture, because we have to be able to grab the right I from here. There is one other way to calculate I, and it's called the parallel axis theorem. I will cover that in the next video. So I, rotational inertia, always related to how easy or hard it is to get any object to change its rotational motion. So to get it started to rotate or stopping it from rotating, either way.